Okay, well, if you were afraid we were done with carboxyl groups, we're not, so hooray. The new thing is esters. And an ester is what happens when you have a carbon chain ending in a carboxyl group. And now, in the last section, we were seeing carboxylic acids where we just put an H over here. But what happens in this case is instead of an H, we have more carbon chain. So something carboxyl group, something else is what makes it an ester. It's two things held together by a carboxyl group. Now, naming these is really not too bad, I promise, except the the slightly weird part is that the naming goes from right to left. The first part of the name that you're going to see is this chain over here on the right, the part in red. Because here's what happens. We have this chain, and you've already learned what to call this blue thing. This is 4 carbons, which means it's probably something about butane. And when we were doing the acids, I told you that when you have a butane with a carboxyl group on the end, we call it butanoate. That part really is butanoate. Now, the burning question is when you have a butanoate or anything else with a COO is, what's on the other end of it? And the answer is 3 carbons, which we call one is methane, 2 is ethane, 3 is propane. When it's attached to something else, we call it a propyl group. So this example I have here, we would call propyl butanoate, or propyl butanoate if you like. So this part you've already seen. This is the part which owns the carboxyl group. It's got the 2 oxygens attached to it. And then this is the continuation. It's what happens after the COO. And those two things together make the name. We don't normally give you a lot of branches in these because the names are difficult enough already, but definitely you need to get these 2 parts right. So remember, the part that's named O8 is the part which contains the carbon with the split, the carbon that's attached to both oxygens. So identify that part first, and that's like your primary. And then this is like a branch connected onto the other end. Let's wade into some examples and see if we can actually do this. I'll keep this example up just in case you want to glance at it, even though we'll have plenty more examples in short order here. All right, so for this thing, our primary is the part that's connected to both oxygens. That would be this. It's connected to that oxygen and to this one. This contains 2 carbons, so that makes us think ethane. When it's a carboxyl group, we call this ethanoate or ethanoate. And the other part of the name comes from what's after the carboxyl group. Well, there's a single carbon here. This is a methyl group. And so this chemical is methyl ethanoate. Not too bad, I hope. Try a few more. Okay, here's our double oxygens. So everything connected to those oxygens is the primary. All that is our primary. 1, 2, 3, 4, 5 carbons is pentane, so pentanoate or pentanoate. Pentanoate. And now they ask, what's on the other side of that? Here's the double O, that's always a dead end. There's nothing attached to that. Here's our O, and again, just 1 carbon, so methyl pentanoate. Here, there's the carboxyl group, so here's the carbon chain that is primary, the one that's connected to both oxygens. It's 3 carbons long. 3 carbons is propane, so propanoate or propanoate. What's after the carboxyl group? 2 carbons. 2 carbons is ethane, but when they're a branch on something else, we call them an ethyl group, so ethyl propanoate. They keep getting bigger, don't they? Okay, find the carboxyl group first of all. There we are. The carbon that's connected to both oxygens and everything before that, that's our primary chain. 1, 2, 3, 4, 5, 6 would be hexane. With this connected to it, it's hexanoate or hexanoate. What's after the carboxyl group? Well, the COO doesn't count. That's already covered. 3 carbons. 3 carbons would be propane. If it were a standalone, as a branch, it's a propyl group. Propyl hexanoate. Find the carboxyl group. Here we go. Oh, goody, branches. It'll be okay. It's going to be okay. All right, how many carbons have we got in this thing? 1, 2, 3, 4, 5. That should be pentane, but with a carboxyl group on the end of it, it's pentanoate. But wait, there's more. There are 2 methyl groups attached to this. So it's not just pentanoate, it's dimethylpentanoate. And where are those methyl groups? Remember, this is carbon number 1. So that's 2, and that's 3. These are 3 and 4 are where the methyl groups are attached. So 3,4-dimethylpentanoate. Now, all that is just the primary chain on the left. We still have the question, what's after the carboxyl group? What's on the other side? On the other side, we have 1, 2, 3 carbons. 3 carbons would be propane, or when it's a branch, a propyl group. Propyl 3,4-dimethylpentanoate. Line structural. Okay. Here's our carboxyl group. So this carbon belongs to the primary chain, and so does that one, and that one, and that one. Total of 4 carbons. 4 carbons is butane, or in this case, butanoate, or butanoate. And what comes after? After the COO, we have carbon, carbon, carbon. It's a propyl group again. A lot of propyl today. Good. And they're really going for it with the last couple. Here's our carboxyl group. So the primary has to contain that carbon, and I could take either one of these. I'll go with this, just to make it relatively straight. So how many carbons is that? 1, 2, 3, 4, 5, 6. 6 carbons is hexane, or with a carboxyl group on it, it's hexanoate or hexanoate. But it's not just hexanoate. We've got these extra things on it. There's a methyl group here, a methyl here, and a methyl here. So it's trimethyl hexanoate. And even that isn't enough. We have to say where these methyl groups are. That's carbon number 1, the one that's connected to the oxygens. This is 2, this is 3. So we're going to get 4, 4, 5 trimethyl hexanoate. 4, 4, 5 dash trimethyl hexanoate. All that is our primary chain, or is the left side, the part before belonging to the carboxyl group. What's after the carboxyl group? A humble methyl group. Methyl 4,4,5 trimethyl hexanoate. And now, let's see, there's a carbon there, and there. Is that 5? Yeah, 5 carbons on the left. So 5, it would be pentane or pentanoate. Pentanoate. There's no branches or anything to worry about there. So now our question is, what's after the carboxyl group? Well, this line, on this end, it's got an oxygen because it specifically says so. This end, unlabeled, means there's a carbon there. a single carbon, meaning methyl. This is methylpentanoate. Can we draw these things? Maybe. Let's try. Pentanoate. Oh, hey, we just saw this, didn't we? Let's see if we have 15 seconds worth of working memory. Pentanoate means pentane, so 5 carbons. 1, 2, 3, 4, 5. The O8 means it ends with a carboxyl group. There we go. And what's after that? A methyl group. So this methyl goes there. No big deal, right? I mean, it's a little bit odd that we normally draw these, like the first thing you see in the name ends up being the last thing you draw in the diagram, but we've been doing that for a while. We're used to skipping over stuff at the beginning of a chemical name and saying, okay, I'm leaving you behind because it's more important to get the primary chain down first. So I hope that doesn't throw you too badly. When we look at this, we go, okay, methyl, you can wait. Pentanoate is the core. That's the primary chain. I'll get that down first, and then I'll worry about all the little bits stuck on around the outside of it. So, fair enough? I hope, probably. Let's try a few more. Heptyl, that can wait. Methanoate means a single carbon. Okay, so there's methanoate. What's attached to it? Heptyl, as in heptane, means 7 carbons, means I probably want some more space. Let's scoot this over a bit. So there's methanoate, methyl methanoate, ethyl methanoate, propyl methanoate, butyl methanoate, pentyl methanoate, hexyl methanoate, heptyl methanoate. That should do it. Butyl ethanoate, so ethane, 2 carbons. Carbon, carbon, carboxyl group. By the way, if you do the double bond down and the single bond up, it's not going to break anything, but almost everybody draws them this way with the double up and the single down um, for no particular reason. Just expect to get some funny looks if you ever switch this around, even though technically it's not incorrect. It's just not the way that most humans are used to drawing them. Okay, so there's ethanoate, and now a butyl group. Methyl ethyl propyl butane is 4 carbons, so C, 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 C. And of course, there's hydrogen around all this. I'm leaving that out too, because it saves about 5 minutes per video if I don't do the hydrogens. But certainly they are there. And to figure out how many, you just say 4 bonds for each hydrogen, or sorry, 4 bonds for each carbon, see how many are already used up, and then populate all the remaining ones with hydrogen atoms. Propyl octanoate comes from octane, so 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. That's octane. Now it's octanoate. And what's on the other side? A propyl group. Propane is 3 carbons, so 1, 2, 3. Not too bad. A few more. They keep making them crazier. Butanoate or butanoate. Butane is 4 carbons. 1, 2, 3, 4. So there's butanoate. Now, it's not just butanoate, it's 3,3-dimethyl butanoate. So that's carbon number 1. Number 2. Number 3 has a couple of methyl groups on it. There we go. And on the other end of the carboxyl group, it's ethyl, 2 carbons. Ethyl octanoate found in oranges. The reason we care about a lot of esters is that they're found in food, and in a lot of cases, especially fruit, the esters are what make them smell the way they do. So strawberries, oranges, I think lemons and apples, bananas, all of those have esters in them that our noses are sensitive to. I mean, there's a gazillion chemicals in a fruit, but there's only a few that our noses are good at picking up. It turns out our noses are pretty good at esters. And so a lot of these esters are recognized as that chemical that smells like strawberries, or in this case, that chemical that smells like orange. Ethyl octanoate is the orange smell, and octanoate means 8 carbons, as in octane. 4, 5, 6, 7. There's octane. Now it's octanoate, and what's on the other side? An ethyl group, meaning 2 carbons. Well, that wasn't so bad. What's happening with this? 2-methyl propyl methanoate. Okay, well, let's start with our primary and we'll worry about that weirdness in a second. Methanoate means methane, so there's methane. Now it's methanoate, and this can't be like propyl methanoate. This can't be about the primary chain because they aren't giving numbers for it. Well, or would they need to? I think all this is the continuation. All of it comes out in the end there. So I believe this is methanoate is our primary on the left, and now we have propyl methanoate, propyl group here. So this would be propyl methanoate, and now they're saying 2-methyl means this actually has a branch on it. That's rare. We don't practice those very much, but this is my call for what this thing looks like. 2-methyl propyl is all the stuff after the carboxyl group, and the primary is the methanoate part. Okay, there was just, if you saw a little blip there, it's because I paused the recording to check on this. I wasn't entirely confident about this one, but the funny thing is, I am now confident that this is correct, and I believe there is a glitch in the answer key, and it's a weird glitch. It's not anywhere that you would expect it to turn up. The answer key shows, I'll sketch it out, as the answer for this one. I'll reproduce this as closely as I can to their picture, and then we'll talk about what I think is the matter with it. They go carbon, double bond oxygen, they go straight up with it, which is no big deal. They have O, CH, they write CH2, and then a C, and then they do a split here. And they also have a C here. So this part matches what I have. I mean, mine is shaped more like a T and theirs is shaped more like a Y, but it's still a line of 3 carbons, like there, and a single carbon splitting off. So I agree with them about that. That's the 2-methyl propyl part. The weird thing is, this says methanoate, meaning only a single carbon on the left, meaning it should look like this. In their case, they seem to have mistakenly put an extra carbon on here. What they drew would be 2-methyl propyl ethanoate. No good. So if you take that C off, which I'm very confident is a mistake, then we do have the same structure. So methanoate means a methane with the carboxyl group, and then 2-methyl propyl, all mashed together into one word like this, is the continuation afterwards. Getting a little spicy right at the end. Okay, last thing. This is just a detail about where do esters come from, and it turns out you make esters in a way that makes sense because of the other molecules that we've studied. How do you make an ester? Well, esters have a carboxyl group in them, and it turns out you can make one by mixing a carboxylic acid and an alcohol. So let's set one of those up and see what happens. Here's a carboxylic acid. This would be ethanoic acid because it's got 2 carbons. Ethanoic acid. And the other ingredient we need for this, I'll go orange, is an alcohol. And let's go with propanol. And OH, propanol. We used up all the ethanol, we use propanol instead. Okay, so ethanoic acid, as in vinegar, mixes with propanol. Here's what happens typically. When these react, this is an acid which wants to give away a hydrogen. So that hydrogen is liable to come off. Over here is a hydroxyl group, in other words, a hydroxide, which thinks, hydrogen, very interesting. I react with that. I worked a few summers as a base once. I know how to react with hydrogen. If these two pieces both break off, you get OH combined with H. Those two combine to form water. The acid wanted to give away a hydrogen anyway. Once a hydrogen's released, this OH wants to react with it so badly that it actually tears off the alcohol, and you get a water molecule. And what does that leave? Over here you get C, C. We get an ethanoate, which just lost its hydrogen. There's an empty space here where it seems like there should be something connected. Right next to it, we have the alcohol, which just lost its hydroxide, so it looks like C, C, C. And it's got a gap here where it feels like there should be something connected. And this is, what is that, a propyl group? And these two molecules say, well, why don't we connect like that? And when you do, that's how you get an ester. Very often it's an acid and an alcohol met. These two pieces broke off and tackled each other, and you get a water molecule from that. And then these pieces say, well, I've got a free electron, you've got a free electron, why not? If we link up, we will form, in this case, propyl ethanoate. But this would work for any carboxylic acid because they've all got a hydrogen to give, and it would work for any alcohol because they've all got an OH to give. Any of those can react, and you'll get water plus an ester.